Here's the second video of chapter 13. So we left off talking about what factors affect solubility. We already looked at intermolecular forces and like dissolves like. Pressure, once again, it does not affect the solubility of solids and liquids. So for example, if you have sweet tea, you're not concerned whether someone puts the top on really well because it's not going to affect the sugar being dissolved well. It has nothing to do with pressure. Whereas if you have a soda, you're going to want the top to be put on well because there's a gas dissolved. So the carbon dioxide that's dissolved in the drink needs pressure in order to remain dissolved. So what we know the trend is for gases is that increased pressure above that solution will increase gas solubility. So here we have Henry's law, which is an equation that helps us kind of quantify the solubility of a gas under different pressures. So here, Sg is just solubility of the gas, K is a constant, and P is the pressure above the solution. So here, calculate the concentration of CO2 in a soft drink. We know the pressure above is 4 atmospheres, so that'll be the PG, and we're at 25 degrees Celsius, which doesn't play a role here except for the given K value, and the constant is 3.1 times 10 to the negative second. So we plug in K, we plug in pressure, and here is our overall solubility at that time. Solubility, you'll notice, is moles per liter. It's the amount of moles that can be dissolved in every liter of solution. Temperature also affects solubility. So for solid solutes, such as sodium chloride, so table salt, or sugar, or any ionic compound, in general, if we increase temperature, we're going to increase the amount that can dissolve. Whereas for gases, it's actually the opposite. If we increase temperature, think about those gas molecules in the Coke. They will begin moving more quickly and exerting greater pressure, and therefore they're going to escape the solution. And that will in turn decrease the solubility of that gas. So if you increase temperature, you will decrease the amount that will be dissolved. Liquids are not as affected by temperature. Like if you think about creamer, it does fine in hot coffee and it does fine in cold coffee. So really we only have a trend for solid solutes and gaseous solutes. There's lots of different ways of expressing how concentrated a solution is. Concentration is really just another word for how strong a solution is. So mass percentage is given here. Mass percent is calculated by taking grams of solute over grams of solution. What's important to note here is the solution is made up of the solute and the solvent. So we've got to have the combined mass on the bottom here times 100. So here, what's the mass percent of sodium hydroxide? If you have 8 grams of sodium hydroxide in 50 mils of water. Remember with water, density is always 1 gram per milliliter. So if you've got 50 milliliters, that means you've got 50 grams of water. So for mass percent, we take the amount of solute, which is the lesser amount, correct? Because that's the minority component. So we've got 8 grams on top over the total solution, which is 58 grams, times 100. And we get 13.8%. Mole fraction, we saw this last chapter, but just as a review, you would put moles of whoever you're concerned with over the total moles in there. So if it was salt water, you'd put moles of salt on the top and the moles of salt and water on the bottom. And it's a fraction, not a percent, so we would not multiply by 100. For us, the most common concentration for us to run into is this thing called molarity. Molarity is shown by a capital M, and it equals moles per liter. So your units can either be just that, moles per liter, or just molar, which we show as a capital M. So it says calculate the molarity of solution by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. So we just have to use what we're given to get these two things. We have to ask ourselves, what's the moles and what are the liters? The moles is of the solute, of whoever has been dissolved. So we're going to take the 23.4 grams of the solute and change it to moles using our periodic table and finding the molar mass here. So we know that there's 0.165 moles of solute It's been dissolved. And the solution has a total volume of 125 milliliters. We've got to convert that to liters by dividing by 1,000. So we get 0.125 liters on the bottom. And our molarity comes out to be 1.32. You can either say moles per liter or just capital M for molar. Here it says, what are the molar concentrations of each of the ions present in 0.025 molar aqueous solution of calcium nitrate? Aqueous solution just means you're dissolved in water. Here's my formula for calcium nitrate, and it actually goes ahead and gives me the formula, or the concentration. Remember, this is moles per liter. Well, look at the formula here, and for every compound, you get 1 calcium. So does it make sense that however many moles of this compound you have, that's equal to the number of moles of calcium? So calcium ions will have the same concentration as the original compound. Whereas nitrate, you're going to get 2 nitrate ions for each compound. So the concentration of nitrate ions is actually going to be double this concentration, which will be 0.050. While I'm here, these brackets is a way of representing concentration. Generally, molarity is what we're going to be working with. So if you see brackets around an ion or a compound, that's just indicating that we're talking molarity and concentration. How many grams of sodium sulfate are required to make 0.350 liters of 0.500 molar sodium sulfate? So as soon as I see this capital M, I know I'm working with molarity. I know the equation is molarity equals moles per liter. So I plug in what I know, 0.500 molar. I take my liters, put it on the bottom, cross multiply so that I can find moles of my solute. I get 0.175 moles, and then I convert it to grams using the molar mass on the periodic table. Solutions are oftentimes created by using dilution. What dilution is doing is you take a really concentrated solution and you add water in order to decrease the concentration to whatever you want. Like for iced coffee, if you have a concentrate of coffee, you take a little bit of it and then you add enough water to make the concentration that you're looking for. So we have equations that help us figure out how to dilute a substance or a solution to exactly what we want. There's 2 equations that really are the same. M1V1 equals M2V2. This is molarity and volume of the concentrated solution, which is the original. And then this is molarity and volume of the diluted substance or the solution after we've added water. So V will go up because volume will go up as you add water and molarity will come down. C1V1 equals C2V2. Same exact premise, except this C just means concentration more generally, where it doesn't have to be molarity. It could be percent by mass, for example, would also work in that. You can use any units on both sides. Of course, molarity needs to be in molarity, but volume could be milliliters on both sides or liters. Just make sure that they match each other. It also doesn't matter which side you choose for concentrated and which side you choose for diluted. You've just got to make sure you pair the correct concentration with the correct volume. So how many milliliters of 3 molar sulfuric acid are needed to make 450 milliliters of 0.1 molar sulfuric acid? So here what you'll notice is the 3 molar is the higher concentration, and that's our concentrated one. We are going to add water to that to make the final concentration come down to 0.1, and we're trying to make 450 milliliters of this diluted one. So we've got to make sure 450 and the 0.1 go on the same side of the equation. And then on the other side, I started with a 3 molar concentration, and I'm looking for the volume. So really we just divide by 3 on both sides, the molarity cancels out, and we come up with milliliters. So what this tells me is I will need 15 milliliters of the strong stuff, the 3 molar acid, and I'll add water to that 15 milliliters until I make a total of 450. Once I get to 450, I can be confident that my new solution will have a concentration of 0.1. We also see these concentration calculations come into play with chemical reactions when we're working with solutions. So here, remember, we already know how to go from grams to moles. We also know that if you have a balanced equation, the coefficients will always be mole-to-mole ratios. So what we really want to do is just use what we know and always get to moles first. So what I kind of like to do is just tally up what I know from a problem and list it on the chemical equation and then figure out where to go from there. So it says how many grams of calcium hydroxide, so I'm going to put question mark grams there, are needed to neutralize 25 milliliters of 0.1 molar nitric acid. Okay, well, if I'm trying to get to moles of something first, you see what you know. Well, I don't know anything about calcium hydroxide yet, but nitric acid, I know molarity and I know volume, which means I can use the molarity equation to figure out moles of nitric acid, which is exactly what I want to do. I want to get to moles of something. So I plug this in. Whenever I'm using the molarity equation, I've got to use liters, so I had to convert my 25 milliliters to liters. I cross multiply to get moles of nitric acid. Now that I get to moles of him, I can hop over to moles of who I care about. So I take moles of nitric acid and I put that on the bottom, moles of nitric, and moles of calcium hydroxide on the top. And I know that's a 2-to-1 ratio. So 2 moles of nitric acid to 1 mole of calcium hydroxide. I could stop there, but I do know that I need to get on to grams. So I'm just going to go ahead and tack on the second conversion factor. And moles of calcium hydroxide come to the bottom. And the molar mass of calcium hydroxide from the periodic table goes up top. I multiply and divide by the bottom. And I get the grams of calcium hydroxide. This is really helpful because if I needed to neutralize this acid before putting it down the sink, I now know exactly how much calcium hydroxide to add. Here's another similar problem. So it tells me 45.7 milliliters of 0.5 molar sulfuric acid is required to neutralize 20 mils of sodium hydroxide. And what is the concentration of that sodium hydroxide? So I'm looking for molarity. I know how much I had of him. And sulfuric acid, I know both volume and molarity. So you ask yourself again, how can I get to moles of something? So start with who you know the most about, which in this case is sulfuric acid. I know molarity. I take my milliliters and to convert it to liters. I'll cross multiply to find moles. So that's always my first step, is get to moles somehow, some way. Here's my moles of sulfuric. I'm going to then use the coefficients to hop from whoever to whoever. So I'm trying to go from sulfuric acid to sodium hydroxide, a 1-to-2 ratio. Here are my moles of sodium hydroxide. I'm going to try not to round too much until the end of the problem. These are my moles of sodium hydroxide. So now you know 2 things about sodium hydroxide. You know the moles that were present, that's what you just calculated. And the problem told you the milliliters, which I can convert to liters. And once I get there, moles per liter will give me my molarity, which will be my concentration of sodium hydroxide, which comes out to be 2.29 molar sodium hydroxide. One last one here, which is really similar. What's the molarity of sodium hydroxide? If we've got 48 milliliters of it, and that will neutralize 35 mils of 0.144 molar sulfuric. So we once again ask ourselves, how can we get to moles? So I'm going to start with sulfuric because I know more about it. Molarity in liters, cross multiply to get moles. I use the mole-to-mole conversion using the coefficients. I get to moles of sodium hydroxide. I kind of regroup and see, what do I know? Well, I know moles of sodium hydroxide. My problem gave me volume. So I can now divide to figure out the molarity of that unknown solution.